Check it out now, y'all.
NanoHub U, online instruction.
Hi, we're back again, and this time we're going to discuss the eigenfunctions of Schrödinger's equation. I'm going to try and give you some understanding of what the solutions are for these differential equations. So if you recall from our last lecture, we had ended it by reducing this very long, complicated differential equation into three separate differential equations. Each of these three differential equations depends only on one of the three coordinates, r, theta, or phi, for the hydrogen atom problem. There are two constants that have been introduced to get the problem to this stage. One of these constants is m squared, right? We're gonna need to come up with a way to evaluate what the possible values of m squared are. And the other constant that was introduced was this quantity L times L plus 1, right? And we're gonna need to come up with a way to evaluate what these values are for the script L that appears in that equation. So let's begin with the first equation. That's the simplest of the three to discuss. This equation for capital phi is a pretty simple differential equation, and the solution can almost be guessed at, right? Because you can just try a few different functional forms, and you very quickly realize that this e to the im phi is going to satisfy this differential equation. So so the standard answer is the eigenfunction for the phi dependence of the Schrödinger's equation is given by e to the im phi, where m is some constant. What we need to do is we need to come up with a condition to evaluate what m is. And the way we do that is by realizing that if we rotate this wave function e to the im phi, if we rotate it through a complete 2 pi radian revolution, right, we'll end up back at the same value that the wave function should have had when before the rotation. So if we pick a point in space and it's displaced by this angle phi, and we add 2 pi to phi, we end up back onto the same plane. And if the value of the wave function at this point is going to be precisely equal to the value of the wave function at this point, then we require that the wave function be single valued, and that statement is made right here, right? This is the single valued criterion, and that just simply means that if you increment the variable phi by 2 pi, you should get back to the exact same wave function you had before, and that implies that this e to the 2 pi m is equal to unity. And the only way that can be true is if m is equal to a signed integer. So small m can be equal to either 0, plus minus 1, plus minus 2, and that allows us then to write down the solutions to the phi part of the wave equation, where we fixed this quantum number small m by this single valued criterion. It's kind of useful to think about what the physical significance of this phi wave function is, and I won't go through this in detail because this will come out in next week's lectures. But I'll just make the comment that there's a very strong parallel between linear motion and orbital motion. We tried to make that point in the early part of this course, where we wrote down the equations of motion for linear motion and rotational motion, and there was a one-to-one analogy. For every quantity in linear motion, there was a corresponding equation for rotational motion. You would expect the same thing to hold in the quantum case, right? And the only difference is, instead of translating the particle through a distance x, now the electron is governed by this rotational differential equation, and so the displacement of the phi wave function is through this arc S as the angle phi is rotated. And this leads you to a parallel line of arguments that just precisely follow the arguments that we developed for the linear motion. And at the end of the day, what you realize is that the eigenvalue for the first differential equation for the wave function capital phi, the eigenfunction for that is just m times h bar, and this is interpreted as the angular momentum of the electron in the z direction. So this is just a preview of what's going to come. It just tries to get you thinking about what the physical significance of this quantum number m is going to be. But the important thing is that because m is restricted to signed integers, right, the important new thing in the hydrogen atom is that the z component of the angular momentum turns out to be a quantized value. This is not something that you would see classically. So this will be discussed in much more detail next week. The equation for capital theta is quite a bit more formidable than the equation for capital phi. And I write down, to start with, I write down the equation for capital theta. So we need to find a solution, capital theta, that solves this rather complicated differential equation. All is not lost, however, because in the early 1800s, a mathematician by the name of Legendre considered a differential equation of this form, right? And he was able to write down solutions for this differential equation just purely as a mathematical exercise. In the early 1800s, there was no mention or no thought that this equation would ever be useful in the context of quantum mechanics. It took another 100 years for that to develop. But nonetheless, in the textbooks, there's an extended discussion of these Legendre equations, and in particular, it's the associated Legendre equation that's relevant here, right? And what Legendre was able to show is that for any value of this separation constant, L times L plus 1, for any value, there's a possible solution for capital theta that satisfies this differential equation. The trouble is that most of these solutions diverge. They're infinite when the coordinate angle theta, small theta, is equal to either 0 or pi. And so this divergence is not good. It's physically not relevant to the problem at hand. And so then there's another issue about solutions that do not diverge. What are the conditions on this differential equation to produce solutions that do not diverge? And the answer to that question turns out to be that if L is equal to a positive integer, and if the value of L is greater than or equal to the magnitude of this quantum number m, then you've got solutions that are finite everywhere, and those solutions are physically relevant. So it's this condition that allows us to impose integer values on script L, right? And these integer values are going to be related to quantum numbers that describe the electron state. So the acceptable solutions to this equation 2 for capital theta, right? The acceptable solutions now have to be keyed to the values of script L and M. And so for that reason, possible solutions often are subscripted by the variables L and M, because you have to specify those quantum numbers, right, in order to select out the appropriate value for capital theta. And the different values for capital theta are going to describe different eigenfunctions of the different energy levels for the hydrogen atom. That's ultimately what's going to come out. It's also, in the literature, you'll also find that the solutions for the first differential equation, capital phi, and the solution for the second differential equation, capital theta, those are often combined into one quantity. So you'll find very often that these two solutions are combined to give you a quantity that's known as the spherical harmonic. The spherical harmonic is a function of the angles theta and phi, and that spherical harmonic has to be subscripted with the integers L and M, because those integers then specify the appropriate form for capital theta and capital phi, right? So depending on which textbook you're reading, you'll find solutions for capital theta and capital phi listed separately, or you'll find the wave function called capital Y, right? And they're all related by the equations in this box. It's useful to list some of these solutions in a table form. This makes it easy to use in the future. And so what I do here is I just copy the table that's in your textbook. There are values for script L. These are integer values, 0, 1, and 2. There are values for small m. Very often, small m is also subscripted by this parameter L, and that'll become clear later in the semester. But small m always has to be less than script L, and m can be either positive or negative, as you can see. And so for each choice of L and m, you can then just read off directly what the solutions of Schrödinger's equation are, right? In terms of these are the Legendre polynomials. The physical significance of this wave function for the physical significance of this differential equation for the wave function capital theta is discussed in this slide. And I just want to make the point that there's often a new operator that's defined that sort of allows you to appreciate what the integer script L is representing. So if you take Schrödinger's equation, this is the form that we derived in the last lecture. You can slightly rearrange it just by straightforward algebraic manipulations. And what you find is this very complicated term enclosed in these magenta brackets. This very complicated term in the magenta brackets is often defined as an operator, L squared. You know L is an operator because it's got that little funny symbol above it that signifies an operator. And of course, by making this definition, right, then you can substitute this operator L squared back into Schrödinger's equation. And what you find is that Schrödinger's equation can be written in a really transparent form now, right? The first term is related to the momentum of the electron in the r direction. The second term, with this definition for the operator L squared, is now an angular momentum energy, right? So this is the kinetic energy tied up in the angular motion of a particle. And then the third term is just the interaction potential energy due to electrostatics, right? And so these three terms multiplied by the wave function psi is equal to E psi, right? And these wave functions psi, of course, are what we're talking about in this lecture. But with this definition for script or for the operator L squared, you can show that if you operate on the eigenfunctions y sub Lm, you get back this separation constant L times L plus 1 times h bar squared times the wave function back itself again. So this in itself is like a separate eigenvalue problem that's embedded in Schrödinger's equation. And this operator L squared is interpreted as the square of the angular momentum operator, and it describes the angular momentum, the magnitude of the angular momentum that the electron has when it's physically bound to the proton to form the hydrogen atom. And what this equation is just saying is that this angular momentum squared can only have quantized values, and those quantized values are given by this quantity L times L plus 1. times h bar squared. So this form of the eigenvalue problem with this definition for the operator L squared, this justifies this way of writing the separation constant as L times L plus 1. This introduction of the separation constant in that funny form is strictly driven by this realization. So I will say also that this will be discussed in considerable length in next week's lectures. So we'll come back to this angular momentum eigenvalue problem and explore the consequences of these quantum numbers. So that's about all I wanted to say about the wave function for capital theta. I'll say that there's an extended appendix in this lecture where I list all these Legendre polynomials and I go through the discussion of the Legendre equation. So for those of you that really want to see the details, all that stuff is put into the appendix, and if you have time, you can take a look at it. You will not be required to understand all that mathematics, but you will be required to understand the significance of these values for script L and how these values for script L are tied in with the quantum numbers small m. The third part of this discussion involves the solution of the radial wave equation. This is the equation for the wave function capital R that was introduced. And capital R has to satisfy a differential equation that looks like this, right? So this differential equation contains the script L times L plus 1 term, and it also contains the definition for the interaction potential energy U of R. So again, this is a formidable looking differential equation. The solutions of this differential equation are not obvious, but again, there was a famous mathematician by the name of Laguerre, and in the late 1800s, he, just as a mathematical exercise, discovered the solutions to an equation that looks very similar to this. So this discussion of the Laguerre differential equation I've also put in the appendix of this lecture. It's an extended discussion with a lot of mathematics. It tries to lead you through the various steps. You don't have to understand or master that arithmetic to understand the consequences of it. And what we're going to do in this lecture, of course, is we focus on the consequences of the solution to these differential equations, and we rely on Laguerre's mathematics to tell us what the functional form for capital R must be. So the interesting thing that comes out of all this arithmetic is that there are only certain energy values E. Once script L is specified, there are only certain values of energy E that satisfy this particular differential equation. And these allowed energy eigenvalues are going to be indexed with another third quantum number, small n. So n is going to be the third quantum number that we introduce into this discussion. And this quantum number n is going to then tell us what the various energy eigenvalues are for the radial differential equation. I will say up front that there are two ways of writing the radial differential equation. This was discussed in the appendix of lecture L3 earlier this week, right? The two forms of the radial differential equation that you find in different textbooks I've written down here. And this gives rise to a new definition. So very often you'll find textbooks that define a new radial wave function, capital P, which is equal to the radial wave function capital R times the coordinate position small r. And you can see why this definition follows. It's motivated by the first form of this differential equation. And so very often you'll find this differential equation written in terms of capital P in this form, right? And so depending on which textbook you read or which website you might refer to, you could see either one of these two differential equations. They're equivalent. And furthermore, this first differential equation is often written in terms of the wave function capital P. The wave function capital P and the wave function capital R are related to one another by this simple equation. The other thing that follows from this discussion is that the eigenfunctions for this differential equation have to be labeled by script L, because depending on what value you put for script L, you're going to have a term here, right? That the solution is going to depend on that. And it's also going to depend on the quantum index n, because that's going to specify the energy eigenvalue. So these solutions all are subscripted with indices that you have to first specify what n and L is. Once you specify n and L, then you can just look these solutions up thanks to Laguerre. So again, I just copy the table that's in your textbook. I display it here. Your textbook uses the notation capital P rather than capital R. They give the wave functions for capital P. You can get the wave functions for capital R simply dividing by the radial position small r. So that's taken care of. It's pretty straightforward. And you can start to see that these radial wave functions, they have a common feature. All of them depend exponentially on the radial distance from the center, from the location of the proton. So all these wave functions decay exponentially to 0 as r gets big. And of course, this is something that you should have come to expect based on your expectation for wave functions, right? The wave functions always tend to go to 0 as you get far away from the quantum system of interest. I plot a few of these wave functions just to make that point. There's actually two forms of the wave functions. Those forms depend on the value for script L. When script L is equal to 0, the wave functions all have peaks. They all peak up at r equal to 0. Right, and as r gets larger, right, the wave functions exponentially decay to 0. You can see that these wave functions undergo an oscillatory behavior. So for the second energy eigenvalue given by the index n equals 2, right, you can see that the radial wave equation comes down, crosses 0, and then approaches 0 from below. If you take the n equals 3 energy eigenvalue for L equal to 0, you can see that there are actually two 0 crossings of the wave function before the wave function exponentially approaches 0. So you can view these wave functions in many different forms. I give a more exploded plot of the wave function so you can see the 0 crossings in a little bit more detail. There's some very nice plots and tables given at a website, and so you're free to check those out on your own. I think the important point to take away from this, okay, apart from the math, which we're trying to minimize, is that there are three quantum numbers that come out of this discussion. There's basically a quantum number for each of the three equations. These quantum numbers specify phi, theta, and r. They're specified by those three parameters. And the first quantum number, the one that's probably the most important, is referred to as the principal quantum number. That's universally given the symbol small n, and that number is an integer that runs from 1, 2, 3, 4 on up, right? N equals 0 is not a possible value for that quantum number. The orbital quantum number is described by script L, And that orbital quantum number, turns out, has to be less than n-1. L can start at 0, be an integer, but it terminates at the value of n-1. So whatever n is, that restricts the values for script L. And then lastly, the magnetic quantum number, which refers to the angular momentum of the electron in the z direction, right? That's referred to as the quantum number small m. That is restricted to values that are determined by script L, right? So if you specify a value for script L, that immediately tells me what the range of values are for small m. So these are the three quantum numbers that describe the electron states in a hydrogen atom. There's one more quantum number that we're going to have to introduce later on in the semester. That's going to be related to the intrinsic spin of the electron, but at this point in time, we don't want to worry about that particular discussion. Physically speaking, there are simple reasons why there are restrictions on n, L, and m. So I go through this discussion here. It's qualitative, but it tries to give you a sense for why n is restricted to integer numbers, why script L is restricted to values less than n, and why m is always restricted to values less than L. So, if this helps you understand why there are different ranges for the quantum numbers, that's great. It's just a qualitative way to try to understand exactly what's going on. So I got to stop. I'm about out of time for this particular lecture. When you come back, we're going to discuss the energy eigenvalues in more detail. We're going to show you how to calculate those energy eigenvalues. We're going to try to give you an understanding of what these different quantum numbers mean in terms of those energy eigenvalues. So that's the next topic of discussion. So thanks for your attention on this. It's a lot of math. Like I say, if you're really interested in the details, check out the appendices. Bottom line is you should be able to understand and use these quantum numbers in an intelligent way because they're used universally throughout science and engineering. So that's an important thing to take away from this particular lecture. So see you next time.